Now is the time when we answer the pesky question of what do these matter waves actually mean? Does it actually mean that an electron is actually moving like this when it's moving? No, that's not what it means. It means something far more interesting and strange and extraordinary. These waves are not to be thought of as actual, these kind of like what you expect from like an ocean wave or something like that. These waves represent the probability of a particle to be in any specific location at any specific time. Okay, so what does that mean? It means something along the lines of this, right? Let's say that we have a box, okay? And let's suppose that there is an electron in that box. And that electron has a matter wave, right? If it has momentum, it has a matter wave. And that matter wave is given by some function called psi, which is called the wave function. So psi of x is some function that's called the wave function for any matter particle. And every particle has a wave function, and systems of particles have a wave function. You have a wave function. I have a wave function. Quantum mechanically speaking, this is a property of all matter. They have waves, okay? And so let's say that inside this box, there's an electron, and let's say that the wave function looks something like this, right? Let's say let's take a classic sine wave, okay? So this here is the psi of x for this electron. Now, the wave function alone does not determine the probability of finding the particle. It's actually the wave function squared. So if I take psi of x squared, all right, then I am left with some function that gives me the probability of where I may find this electron within this box. So, for example, if I square this sine function, right, so a sine squared function, I'm going to get something that looks like this. This part here is going to be squared, so it's going to be a larger hump. And if I square this negative part of the sine function, I get another hump, right? Squaring anything negative becomes positive, right? So now I have my psi squared function is these two little humps that look like this, right? And what does this mean? This means that I have the most probability of finding that electron. If I'm inspecting this box, right? If I'm using scientific tools to look in this box, then I will most likely find the electron right here at this peak or right here at this peak. Now, do I have to find them at either of those peaks? No. There's also some but lower chance that I'll find it there. And there's also some but lower chance that I'll find it there. Where can I be very confident that I will not see this electron? Here, here, and here, where the probability is 0. Okay, so you can say, I am damn sure I will. If I look in this spot, I will never find the electron. If I look in this spot, I will never find the electron. If I look in this spot, I'll never find the electron. But if I look around here and here, there's a good chance I'm going to find this electron. This is strange. All right. It also implies that electrons aren't what we think they are, aren't what we used to think they are, at least, because if this is the wave function for the electron, and this is the probability of it being located, then before we've actually located and discovered where this electron is, the only interpretation that makes sense is that the electron is not localized. What do I mean by that? It means literally the electron is smeared throughout space over this wave function. Also incredibly strange. So this idea of individual identity of particles is a little bit, loosened. We don't think of these isolated local particles the way that we used to. We now think of them as things that are smeared all over space. And this has, huge implications for atoms, because if I have a positive nucleus, right, and I have an electron orbiting it, this is an entirely inconsistent and untrue model for an atom. What's really happening is this electron has some wave function that is surrounding this particle, or this nucleus, right? And it makes much more sense to think that this electron is really smeared out in space, right? Where there's the most probability of finding it at, whatever radius that it's orbiting at, and then, a little bit less probability of finding it elsewhere at any given time. Okay? So the electrons that are orbiting atoms are not nice localized electrons like we think they are. They're not like a moon orbiting the Earth. They are actually, imagine the moon as if it were smeared out all around like cream cheese around the Earth. That's more accurate way of conceptualizing the process that we're talking about. Okay, now, what do these wave functions have to say about atoms? So if you look at this next slide, you see something very interesting, and that explains why electrons can only be in certain orbitals and why those orbitals are only allowed to have certain amounts of energy. Okay, so here's the way this works. If we have a positive nucleus, okay, and imagine we have some, electron orbiting it, and the orbital is actually like some sort of wave. Obviously, I'm making this, a two-dimensional wave when it's actually a three-dimensional wave. So it turns out that the only orbitals that work are the orbitals in which the wave function allows for one full or integral number of wavelengths to fit in the orbital. Okay, so I'll make this a little bit more clear. If you go to the next slide, it says another way to look at it. You see on the left, there is this allowed orbital in which a whole number of wavelengths fit snugly inside that orbital. All right? But if there is any orbital, any radius around that atom such that the waves do not perfectly line back up once in other words, it's not a whole number of wavelengths that fit inside that orbital, those orbitals are unstable and not allowed. You'll never get it. And so this explains why you have the famous n equals 1, 2, 3, 4 orbital that you get in like the classic Bohr atom. So 2 slides from now, you'll see, maybe you've seen this in chemistry before, where the energy levels of any given orbital in a hydrogen atom are given by negative 13.6 eV over n squared, where this is in electron volts, not joules, right? So the whole question of why these energy levels and why these orbitals, where n equals 1, 2, 3, 4, it turns out, and this can be derived very easily, but it turns out that these energies apply to only the orbitals where an integral number of wavelengths will actually fit inside the orbital. All right? This explains all that chemistry that you've learned up to this point that you're like, well, why do they choose that orbital? Why does that make sense? Why is there these precise amount of energies for each orbital? It's because, once again, every electron has a wave function, and if that wave function exists such that there's a whole number of wavelengths that fit within an orbital, you have a stable orbital for some given atom. All right. And it turns out that for the n equals 1 state of the ground state of a hydrogen atom, there is a classic radius called the Bohr radius, which is, Bohr radius is equal to 0.053 nanometers. All right. Okay, that's the radius of roughly a hydrogen atom. How do we know that it's not exactly that, and that's kind of an approximation? Once again, because the electron is actually smeared all over space, and you can't really say there's one precise radius because there's always going to be some variation in the possibility of the location of that electron. And that also has a little bit to do with this thing called the Heisenberg uncertainty principle, right? An electron cannot be in a precise radial orbital because that means that you will know its position too well. And the uncertainty principle says there's always some uncertainty and how well you can know the position of an electron. So that is the explanation of why electrons have the orbitals they do and why this first quantum number, this n number that determines the energy level of the orbital, exists. In the next video, we're going to talk about some of those other quantum orbital numbers that maybe have come up in chemistry, like L and M, and what are those referring to, and how do they fit into this whole quantum mechanical model. I'll see you there.